Mm. Okay, you guys should be able to see my screen now. Let me start presenting. Oh, wait. Okay, you guys see the presentation now? Okay, cool. Just give me 1 second. Okay. All right, so welcome to our 11th recitation. And today we're going to be learning about these few things. We're going to be talking about caches, basically, placement policies, replacement policies, general cache organization, and cache design. And so let's jump right into it. So we have also the grades for Bomb Lab are up now, and there was a bit of confusion with them because initially I forgot to upscale it to 120 points, and then the original script also didn't take care of people that did multiple bombs. But I think I fixed it all now, so everyone's grade should be good. And then, okay, so let's start talking about memory hierarchy. So we looked at this last time. So we talked about how the closer you are to the CPU, the faster it is to retrieve the data. And so registers are the closest. Then we have the caches, main memory, and then we have the local secondary storage, such as the hard drives or solid state drives. And then we have remote storage. So, hello. Does anyone have a question? Okay. So we talked about the first few slides are from the last presentation. So we basically covered how the CPU, how registers get things from the cache, and then, well, yeah. So first they look into the cache for things, and then the CPU will go and look into the actual main memory if something's not found in the cache, and that results to either a miss or a hit in the cache. And yeah, so basically, whenever we're looking for a block of memory and it's found in the cache, it's called a hit. But if it's not found in the cache, it's called a miss. And what we have to do is go and get it from main memory because it wasn't in the cache. So we get it from main memory, and then once we get it, we want to put it into the cache, and then next time it'll be available for us to use when we need it again. And that's basically the main concept of a cache. And so yeah, we talked about these cold misses, conflict misses, and capacity misses. So basically a cold miss is when there's nothing in the cache at all. And then we have a conflict miss when something replaces another thing, and we actually need the thing that was replaced in another portion of the code. And then our capacity miss is when we're not able to fit as many things as we need into the cache because it's a finite size. So we can only fit so many things. And then we have cache memories. So, oh wait, we already talked about this in the slides before, but basically that's the main structure of a CPU and how it interacts with the cache. It's not very detailed, but this is the high level overview of it. And so in a cache, there are this is the general cache organization. So a cache will have an S number of sets, and the number of sets is usually a power of 2. So it's 2 to the small s sets, and then we also have a number um, EE lines per set. So um, that's basically how many of these boxes are in the purple shaded regions. And that's also usually a power of 2. And then lastly, within each line, we have 3 things. We have a valid bit, and we'll get more into what that is later. And we have the tag bits, which helps us uniquely identify the what's placed in that line. And we also have the B bytes per cache block. So basically, when when the CPU goes to look for something in or wants a specific piece of data, it'll first go look in the cache, and if it's not there, it'll go to the main memory and try to get it. But from the main memory, it doesn't just get that like one piece of data. So if it's an integer, it's not just gonna go get those 4 bytes of data. What it does is it gets a whole block of data. So it might get like 16 bytes, like a 16 byte block from that region that also contains that integer. And so we could have B bytes per block. And so yeah, so that basically stores many pieces of data from memory. And then the final cache size, when we have all of these things, is going to be S times E times B. After we have, so we have the number of sets times the number of lines. That tells us how many total, or the number of sets times the number of lines per set. And that tells us the total number of lines. And then each set contains B bytes of data. So we have S times E times B bytes for the total cache size. And then next up, we have the cache read. So how we actually go get data from the cache, how we find out which data is the piece of data we're looking for. So first, what we want to do is locate. Okay, so let's start off with this here. So the address that we want to get is split up into 3 parts. So we have T bits for the tag, S bits for the set, and B bits for the block. So so basically from there, the first thing we do when we want to get something of this form is we go and check which set it's in. So we use the S bits, and so you see how this is 2 to the small s sets, and we also have small s bits here. So that's done deliberately because you need s bits to in order to uniquely identify each set if you have 2 to the s sets. And we have the same thing here. It's 2 to the b bytes per block, and it's b bits here because then we need b bits to uniquely identify each block and or each portion of the block. So basically, yeah, so first what we do is we go here and look for which set our piece of data is in. And then once we isolate which set it's in, we go through each of the lines in the set and compare the tag bit. And if the tag matches, then in a set, every line has the same set index, but the tag will vary. Yeah. Yeah, basically. But the thing is, yeah, so a line doesn't contain its set index, but yeah, all of the lines correspond to the same set index. And the tag varies based on what you placed in it. So if we placed so yeah, so if what we placed matches what we're looking for based on the tag bits, and the valid bit is and the line is valid based on the valid bit, then we have a hit. And then because after we have that hit, after the tag matches and it's valid, we go and use the block bits to find out which actual piece of data from the block we need. And so yeah, so that's what this little thing I wrote here explains what the block offset does. So we need to know which of the bytes to get. So let's say there are 64 bytes, which is what it usually is in a block. And we need to make sure we get the right data. So the B bits will tell us which byte you want out of the 64 bytes that are in that block. And then we have one extreme version of a cache, which is called a direct mapped cache. And this is where your E, the lines per set, is equal to 1. So we have one line per set. And so this is directly mapped because there's one line per set. And yeah, so in here, when we go and try to find where our data is stored, we go and first what we do is we find the set. And once we found the set, we use the tag bits to find which line contains it. But the thing is, there's only one line per set. So once we found which set it is, let's say it's this second set here, we don't need to iterate through more lines. We just need to compare the tag once. And so in that way, it's faster because you're not iterating through the E number of lines because E is just one. So there's only one line to check the tag of. And if that's good, you just check if it's valid and get the data that you want. So yeah, so this basically just, this is just what I explained here. We check if it's valid, we check if the tag bit matches, and then we just get it based on the block offset. Yeah, so let's say the block offset is points to these these 4 bytes here, then that's what we'll get. And yeah, if in this case the replacement policy is if we find the set and let's say we find some set here, right? And so let's say it's in this set. So this is the line that we're looking at. If the tag of this line doesn't match the tag that we're looking for, we're going to go into main memory, get what we need, and replace this specific line. So that's the replacement policy here because the set bits need to match. And yeah, so then this is the only line in this set. So this is the line that's going to be replaced. And then we have other replacement policies in cases where there's multiple lines per set, because then we have to decide which line we want to replace, right? So this is kind of a little simulation of a directly mapped cache. So let's say this is the configuration of our cache, right? Let's say we have, it's a 16-byte cache. And so we have 4-bit memory addresses. And let's say our B value is 2, so there's 2 bytes per block. And there's 4 sets, and our E is 1. So there's one, there shouldn't be block per set, it should be line, I guess, 1 line per set. But I guess a line contains 1 block, so it's equivalent to saying that. So let's just kind of step through this here and try to look at what's going on. So yeah, so what we do is we first want to look for this piece of data, the 0, 0, 0, 0. And so, okay, so we also have to take a look at this. So in our case here, there's 1 tag bit. There are 2 set bits and 1 block bit in our 4-bit address. So first what we do is we go and look at the set bits, right? And the set bits it's 0, 0. So we go into set 0. We go we go and check if it's valid, and it won't be valid because it's a cold cache. There's nothing. So it's going to be a miss. So this first one is going to be a cold miss. And yeah, so these misses and hits here map to these 1-to-1, but it kind of maps down like that. And then let's say the next address we want to read is 0001. Then we're going to go into the cache. And okay, also when we miss this, what we do is we go and load whatever we didn't find. So yeah, so after we didn't find this, we go into we go into main memory and get the block 01, because our block bit is 0, but we want to access whatever's at we want to get it as a whole block. So we're going to get both block 0 and 1 because there's two bytes per block, not just one. So in this case, our valid bit is going to be 1 because now we have a valid thing in the cache. And our tag bit initially is going to be a 0. So because we can see that the tag bit is 0. And then our block is going to contain blocks 0 and 1 in this case. And then we can go to the next thing. So now let's say we want to get this next address 0001. So what we do is we go and check block 0 and or set 0, and then we check that it is valid. So we'll go and compare the tag, and our tag will the tag doesn't match. So we're gonna need to evict that. Actually, no, sorry. That the tag does match because yeah, because first we look for block 0. Now we look for block 1, and our tag does match. So so it's gonna be a hit because blocks 0 and 1 were both loaded. So we're good in that case. And next up we have this next address 0111, and it's gonna go and check set 3 because that's what 11 is in binary. So it'll go and look at set 3, and the valid bit in this case is going to be okay, so it's going to be a miss because initially it's invalid. The valids are all set to 0 because there's nothing there. It's cold in that area. So it's going to be and then what we're going to do is we're going to go into main memory and go get this the blocks that are there. So let's say this is at block 7. What we're gonna do is we're gonna get blocks 6 and 7, not 7 and 8. And the reason for that is because this is how memory is structured. So we have the 0, 1 and the 2, 3, the 4, 5, the 6, 7, 8, 9. So we're gonna go and we're gonna get blocks 6 and 7, and we're gonna put them there, and it's gonna be a miss because we weren't able to find it. And then for the next thing, this is our address, and what we're gonna do is we're gonna look at the 0, 0, and that maps us to this original set here. And then we're gonna check our tag bit, and the tag bit in this case is a 1, but the original tag bit was still a 0. So it's gonna be a miss because the tag didn't match, and we're gonna go get blocks 8 and 9 from memory, and put them in here, and also set the tag bit to 1 this time. And then we're going to move on because that'll be a miss. And then for this last block, we'll have or for this last address, we're going to check we're gonna check set 0, and again, it'll be a miss because it is valid, but the tag was now set to 1. So in this case, it's gonna be a conflict miss because we removed what we wanted from before, right? So it's a conflict miss, and we go and get it from memory. We get blocks 0 and 1 from memory and put 0 and 1 back here. And then we change the tag back to a 0 instead of 1. So that's basically how we end up with this final state. And yeah, so this kind of gives you intuition for how the blocks are stored in memory and how the blocks are picked out. And yeah, so that's basically it for this simulation here. And then we have our Eway cache. So before, what we had is a direct mapped cache where E equals 1. So, but now let's say our E is greater than 1. And in this case, E equals 2. So if there's 2 lines per set, the main difference here is that we now need a replacement policy because we have multiple lines. So when we go and look for something in here, so we're gonna go in, check if it's valid. We're gonna compare the tag, and let's say it's a match and it's a hit, then we're gonna go get it from the block offset. But we also we have to iterate until the tag will match, and then so in this case we have to go through multiple lines in a set. And the thing here is that let's say we missed, right? So if what we were looking for didn't match and there wasn't a hit, we would have to decide which of these lines to get rid of, or which of these blocks to evict to put in the block that we're gonna go get. And so there's 2 main policies for that. One is LRU, which is least recently used. So the line or the block that was least recently accessed by the CPU is the one that gets evicted, and that's what and yeah. So we put the new block in place of that least recently used one. And then another one is called FIFO, first in, first out. So basically, it's basically how a queue works, and we'll just evict whatever is at whatever was the first thing that was put into the cache at that point. And then next we have, what are we talking about here? Yeah, so here we're basically just talking about the replacement policies. And I just went over this. We have LRU and we have FIFO. And then yeah, so we know how to access something out of here. LRU would be like a stack. Kind of, but yeah, I guess it would be. I think you could implement LRU with a stack. Okay. And then, so the next thing we have is a fully associative cache. So first we talked about a direct mapped cache, which is one extreme, and then the next extreme is a fully associative cache. And in this case, there's only one set. So so because there's only one set, all of the lines that we have are in that one set. And in this case, for the address, there would only be there wouldn't even be a set bits dedicated to the set because there's only one set. We don't need to actually go and look for which set it's in. So all we care about in this case is the bits. And So this can be useful in a case where if you want to allocate more bits to the tag, and you could have more lines that way instead of splitting it up into sets, and that'll give you less tag bits, and so that'll give you a less number of lines. So these are kind of like the trade-offs that you have to think about between the direct mapped cache, the n-way cache, and the fully associative cache. And yeah, so these are basically the three main types of caches that we learn about here. And these are the caches that you're going to be asked to implement in PA5 and basically work with. And here we have an analogy for how locating something in a set works. So the set index is basically, so let's say we compare the cache to a library. So the set index is going to be which bookshelf our book is on that we're looking for. And the tag index will be the title of the book. So we'll find the shelf, and then we'll go through each of the book on that shelf, look for the book with the correct title, and the block index will be the page of the book. So a book doesn't just contain one page, it has multiple pages. So we need the block index to kind of figure out which page of the book we want that we just picked up. And yeah, so we went over this, how the cache size is equal to the number of sets times the number of lines per set times the number of bytes per block. And and then, so let's suppose we're given this configuration here. So we have a 32 kilobyte cache, and we have 64 byte lines. And so basically the 64 byte lines mean that we have our B value is 64, because that's how many blocks there are, or bytes there are in a line. And let's say we have a four-way set, it's four-way set associative. And so we have, and then we have a 32-bit architecture. So our addresses are 32 bits long. So basically what we want to find with this information is how many tag, set, and block index bits there are. And in order to do that, so these are the calculations that we'd have to think about. So if we have 64 bytes per block, that means we have 2 to the 6 bytes per block. So we'll need 6 block bits in order to uniquely identify the part of the block. And then for how many lines there would be in a 32 kilobyte cache, we basically, so to get the number of lines, we have to divide the total size of the cache by the number of bytes in each block, right? Because each line contains, let's say, B bytes, and if the whole cache is C bytes big, then if we do the size of the entire cache divided by the number of bytes in each line, we'll get the total number of lines. And so the size of our cache is 32 kilobytes, and our lines are 64 bytes big. So we could just do, we could use exponents to our advantage to do this division. So we have 2 to the 5th, and then the kilobyte, for the kilobyte, we multiply by 2 to the 10, divided by 2 to the 6. That results in 2 to the 9 lines, and which is a total of 512 lines in the entire cache. And then we have our how many sets there would be to hold those lines. And to calculate that, we basically just take the number of lines, and we know that we have four lines per set. So to get the number of sets, we take the number of lines divided by the number of lines per set, and that'll get us how many sets we want. And that'll be 128 sets in this case, and that's equivalent to 2 to the 7. And we said how all these things have to be powers of 2. Yeah, so this is basically what we just did. And so this leaves us with 6 block bits, as we talked about here, and 7 set index bits because it's 2 to the 7 sets. So how many tag bits are there? We know that it's a 32-bit architecture. So the rest of the bits will be tag bits. So we just do 32 minus the 6 and the 7, and that leaves us with 19 bits for our tag. And yeah, so when we have an address, so let's say we want to read an address like this, right? Like when you guys are working on your code and you have to examine memory or you get a memory leak or something, this is what your addresses look like. So this is in hex, and what we want to do is convert our hex into binary, and we know how to do that. We went over that in the first few lectures and recitations. So you basically just you kind of just convert each digit of the hexadecimal separately and then piece them all together. And this will turn into the binary version of your hexadecimal address. And next up we have, yeah, and then so basically we have 19 tag bits, 17 set bits, and 6 block bits. So so basically the yellow here is the 19 tag bits, the pink here is the 7 set bits, and this gray / light blue here is the 6 block bits. And so that's how we find out which ones are the set, the tag, the set, and the block. And this is how the address is divided up. So you could go into the cache and look at these pieces and find what you're looking for. Hi, Brian. I'm doing pretty good. How you doing? So next up we have writes. So right now we've only been talking about reading, right? But let's talk about writing into the cache. So we have some design choices that we need to make when we actually design our programs and caches. So as our program is running, we have multiple copies of the data, right? So one sec. Okay, yeah. So as our program is running, we have multiple copies of the data. There's the data that's actually in main memory, the data on the disk, and then that same data could be in any one of our caches, L1, L2, L3. And then, so if we make a change in the cache on a piece of data, we need to go back and propagate that change into main memory. And we also need to tell the other caches that this is the change that's been made to this piece of data. So so let's say we're writing to a piece of, let's say we're writing to something, right? So if we want to write to a specific memory address, well, what are we going to do? We're going to go into the cache, see if it's there. If it is, we just write to it. And if it's not, we're going to actually, go into main memory and then get it and put it into our cache and then write to it there. Or we could just write to it straight in main memory instead of ever bringing it into the cache. So hold on, my screen kind of got messed up here. Let me just fix that. Okay. Okay, yeah. So if we have a write hit, right? So if we want to write to a memory address and that that item happens to be in our cache, we have 2 choices. We could either have a write through cache where as soon as we make a change in the cache, we immediately write it back to main memory. Or we could have a write back cache where we defer writing to it until we replace that line. So we'll have a line, and let's say we write changes to it, and then we'll keep those changes. We won't tell main memory about those changes until that line needs to be replaced. And in that case, we're gonna need what's called a dirty bit, because that'll tell us if the line is different from the memory or not. So if the line actually needs to be changed, and or like if that piece of data was changed, and if it was, we need to write back the actual new the new data. And in the case of a write miss, where we look into the cache and it's not there, what we can do is we could either do a write allocate, where we actually load it into the cache and then update it into the cache. And that's a good idea if more writes to that same location are to come. So if you want to write to a memory address and it's not there in the cache, you go and you get it and you put it into the cache. And let's say you need to keep writing to it again. It's better to keep it in the cache and to just keep changing it there. But if that's not the case, then it can no write allocate makes more sense, where you just go to the memory, write whatever you need to write to that piece of data, and don't load it into the cache. And so typically these are the ways that these are paired together. So typically with the write through cache, it'll be no write allocate. And with the write back cache, it'll be write allocate. So yeah, so basically, yes, these are basically the typical pairings, and that's how writes to a cache work, and we already talked about the reads. And then this last slide I have here is talking about it's talking about the Intel Core i7 cache hierarchy. So in the i7, there are different cores. So it's not as simple as just having caches be linked to the CPU, because caches are also linked to different cores in the CPU. And there are actually a lot of different components going on here. So we could have in the i7 and a lot of processors, there's different caches for data and different caches for instructions. And then they'll have this one has a unified cache, which initially contains data and instructions, and then they get split up. Same thing for other cores, for all four cores if it's a quad core processor. And and then there's 3 levels of caches, and all data needs to remain synchronized here as we're like making changes. So if you make a change here, and then this core 3 needs to read that piece of data, we need to make sure that that change propagated back before the core 3 reads it in its cache and finds an old version of it or something. So there's a lot of complications there, and a lot of intricate details that need to be mapped out before a complete cache and CPU is created. So what we went over here is basically a high-level view of the cache, but there's a lot more details that we don't cover in this class, but are very interesting to think about. And yeah, so that's all I have for today's recitation. And I guess we ended about 12 minutes early. And yeah, so if you guys don't have any questions, you can head out. And I'll see you next Tuesday. No problem. Hi, Lulu. If you access the recording from last time, you'll find the answer to that question. Okay, so I'll stop sharing, and I will also stop recording now, and I'll have the recording up by tonight, and I'll also post these slides.